How are you guys doing? Been better. I know. Well, so again, let's take a minute and kind of talk exam format wise. So I've been working on getting the exam together. I think I've got a draft together that I've proofreaded once, so I think that's probably going to be it, short of like small edits to maybe make something go a little bit smoother or whatever. Oh yeah, get it, projector. So the test that I wrote has 120 points total on it. Yeah, if it explodes or whatever, you know. Ooh, happy birthday. Victoria, this one's for you. No. It's very confusing because under the stop by lunch it says 750 on it for whatever that means. So I don't know what that's supposed to mean for you, but anyways, there's 120 total points on the test. You need to complete 70. You can attempt more than 70 points worth of problems. You can attempt all 120 points worth of problems. I find that unlikely to be able to really give 120 points worth of problems an attempt inside of the exam period. I think when I went through, it took me like 50 minutes to do all 120 of them with showing reasonable work. So like that's probably not feasible for you guys. Usually take at least twice as long as it would take me to do something, which is normal, which is really normal. In fact, that's excellent because you're a great group of students. So again, taking the test, should you plan on finishing the entire thing? No, that's going to be normal, right? Could it even be like almost half blank and still be fine? Yeah, for sure, right? So like, it's going to look long. There's going to be a lot of stuff on there. Don't panic about that, right? You only need 70 points for 100%. You know what I mean? So I have 70 points worth of like standalone questions. That means that like your answer it's just like do this, and it says something specific, right? Like find the limit or find the derivative or, like find the maximum or whatever, right? And then there's 50 points of like multi-part questions. So think about the more complicated things we've done, like related rates or optimization or like analyzing the graph. These things that have lots of steps in, possible steps built into them that I can kind of lay some breadcrumbs down for you to help you like through to the finish line on something like that. Particularly for like the setup centric questions, like the related rates or the optimization questions, like I can do things like show that, V is equal to blah, 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 blah formula, so that you have the correct answer when you go to like find dV/dt on the next step. You can, even if you couldn't show it yourself, even if you got that part wrong, you have the right answer. So when you do the derivative, you're differentiating the right thing. So you have a shot at the future answers on it. So I tried very hard when writing those multi-part questions to give you stuff that like a question where it's like, if you screw this up, nothing after it's going to be right or part of it, to make that a show question where you have the correct answer so that if you're doing that further parts, it'll be okay. And again, these 50 points of multi-part questions, like each part has got a point value assigned to it. So like you can do some parts and not finish the question. That's okay. Like do what you know. Everybody's cool? So I like this format because it really allows you to kind of show me what you think you're the best at, right? You can pick out the things that like, yeah, I know how to do that. Yeah, I know how to do that. And when the fan cycle's off, it stops. When the fan cycle's back on because things are getting hot, it's going to squeak again. I know. I know. It's on my to-do list to send another email about it. And then I went through, after I've written the test, I went through and just kind of like compiled a list of topics. So like limit techniques, you should be able to do like the chapter 2 stuff, like direct substitution, or, like multiply by 1 over x on, to the top and bottom, to like, to a point where you can do direct substitution again, or, you should be able to use L'Hopital's rule if that's appropriate. A lot of times the chapter 2 things and L'Hopital could be used interchangeably. So sometimes it might not matter, right? Sometimes the chapter 2 stuff would be easier, sometimes L'Hopital would be easier, but they're just going to kind of be mixed together because most of the chapter 2 problems you could do L'Hopital on anyways, right? You should be able to do you should know your derivative rules, right? So like derivative of sine, cosine, tangent, sine inverse, cotangent inverse, be able to do polynomials, be able to do logarithms, be able to do exponentials, right? You should know all those derivative rules in conjunction with chain product and quotient. Newton's method is what we'll talk about today. So if you're like, what the heck is Newton's method? We'll do that today. It's pretty easy. You should know the limit definition of a derivative. We'll have at least one question on there where I ask you to like use the definition of a limit to find the derivative, or the definition of a derivative to find the limit, or to find the derivative. Jeez, Pete's Mr. Flick. So that's like the limit as h approaches 0 of f of x plus h minus f of x all over x plus h minus x, like that definition. You should be able to do implicit differentiation. Antiderivatives is 4.9, so you should know the antiderivative rules. The good news with the antiderivative rules is they're basically just the reverse of the derivative rules. So like if you know the derivative rules, you kind of already know the antiderivative rules, which is nice. You should be able to use the first and second derivative tests and the absolute min and max test on closed. So this is like the first and second derivative tests are for like open intervals. And then the min max test on closed intervals is for closed intervals. Squeeze theorem, intermediate value theorem, extreme value theorem, and mean value theorem are all things that I'll ask specific questions about. So you should be able to use those things. You don't have to like write down the, you don't have to write down the theorem, but you should be able to use it to like, to do something. Or I might give you an instance where like, hey, I used the mean value theorem to do this, but this isn't actually right. Why did I use it, or how did I use this improperly? So you should know like what do you have to be able to do these things. You should know your definition of continuity and the continuity rules. So like definition of continuity at a point, on an interval, and then you should know the functions that are known to be continuous on their domains, like polynomials and sine, cosine, and exponentials, and the stuff that's like I can just look at it and I tell the form of it and I know this is continuous. You should be able to graph a piecewise function. This came up a bit in chapter 2. You should be able to determine where a derivative fails to exist. So how do you prove that a derivative doesn't exist somewhere? You show that the left-hand limit doesn't equal the right-hand limit, right? So if you look at, if the derivative fails to exist at 0 in the absolute value sense, the derivative from the left is -1, the derivative from the right is +1. Those don't match. That's why the derivative fails to exist there. So you're just using limits. You should be able to do related rate problems, optimization problems, position, velocity, acceleration problems, where you're starting with the position equation and differentiating down to get to the other ones. And then in 4.9, we'll look at acceleration or velocity position problems where you're differentiating up from the acceleration equation to build out your velocity and position equations. But it's kind of the same the same techniques. So the curve sketching stuff where you can like tell where the graph is increasing, decreasing, concave up, concave down, end behaviors, stuff like that. X-intercepts, Y-intercepts. I have end behavior again. That's using end behavior is with a limit, right? The limit as x approaches infinity, and the limit as x approaches negative infinity. You should be able to use limits to prove the location of a vertical asymptote. So if you think there's a vertical asymptote at 1, the limit as x approaches 1 of f of x needs to equal positive or negative infinity, right? That's all you need to show is that the limit is infinite at that point. Should be able to use the increasing, decreasing test and the concave up, concave down test, and be able to find inflection points. So that was kind of the list of the topics here that as I wrote the test and I went back through and I read it, like these are the kind of the topics that fall into. I'll try to get something more together for you guys as we get a little bit closer, but I figured people are probably starting to prep here a little bit and having some test format stuff as to what to expect and some topics of what to expect would be helpful at this point. And I'll get you guys some more as things get a little bit closer. Does that feel okay? Okay. Let's start then today with some questions from homeworks. If you guys got anything for me? Mackenzie. .5, number 61, you say? Sure. So I'm going to just clip this whole little block of problems because I just want to hang on to the directions. It says, find an equation of the slant asymptote. Don't sketch the curve. Okay. Well, if I look at 61, I remember from my Algebra 2 class that for a rational function, like all of these 61 through 64, where I have polynomial divided by polynomial, a slant asymptote is going to exist when the degree of the numerator is greater than the degree of the denominator, which is what I have here. So the easiest way to get that slant asymptote is just going to be using polynomial division. So you can always use polynomial long division. In this case, the denominator is monic, so you could use synthetic division here if you'd like. I don't think it really makes it any much easier, but we could do that. So what I do is I want to start by asking myself, what times x gives me x squared? X. Great. So I put an x there, and then I multiply the x to all of my divisor. I write it below, and then I subtract down. I'll bring down my next piece. And then I'll ask myself, what times x gives me negative x? -1. So then again, I multiply that to all of my divisor, and then I subtract down. Negative x minus negative x is 0. And then 1 minus a -1 is 2. So that's like remainder 2. So what we can say then, now that we've done our polynomial division, is that x squared plus 1 over x plus 1 equals x minus 1 plus 2 over x plus 1. So far, so good with this, Mackenzie? Okay. And this guy here is going to give me the equation for my slant asymptote. So it's the quotient from that polynomial division. The remainder doesn't tell me a hill of beans when it comes to the slant asymptote. But it's just we're going back and we're reusing this Algebra 2 skill, which is like all we really need there. Is that okay? Okay. Sure thing.
So the answer just y.
Yes, what's boxed up is my final answer. Yep. Who's next? Victoria. 41 from 4.4. Sure. So this is just like a regular L'Hopital problem. Boy, that is little tiny, teeny tiny there, huh? All right. So to be able to use L'Hopital, first thing I want to do is check to see that I'm in the indeterminate form, correct? So just a quick little direct substitution. When I plug infinity in for x, I get infinity. When I plug infinity in for pi over x, I get 0. And sine of 0 is 0. So I have 0 times infinity, which is one of my indeterminate forms. So I'm going to go ahead and write this that's written as a product. To be able to use L'Hopital, I have to write this as a division problem. So I would probably write this as that guy. Is everybody okay with that? Okay. And probably easier to think about 1 over x is just x to the negative 1. I'll do that when I do my L'Hopital here. So L'Hopital is now, or it's set up now to be able to L'Hopital it. And again, I'm going to think about this as like pi times x to the negative 1 when I do my differentiating. Okay, the derivative of sine of pi times x to the negative 1 is a chain rule. So the derivative of the outside is the derivative of sine, which is cosine. And then times the derivative of the inside, which is going to be negative 1 pi x to the negative 2. And that's all going to be over negative 1 x to the negative 2. Everybody happy with what I did there? I'm going to simplify now because I noticed that I have some stuff that I can simplify. So I have an x to the negative 2 on top and bottom. I have a negative 1 on top and bottom. And that's great because now I have no denominator left. So what do I have left here? I just have the limit as x approaches infinity of pi times cosine of pi over x, right? If I do direct substitution, this is going to be like pi times cosine of the limit as x approaches infinity of, that's, didn't come up real well, pi over x. And that is 0. Cosine of 0 is 1. So I'm just left with 1 times pi, or pi is my final answer. Is that okay with everybody? Again, you have to be a little bit careful chain ruling with your derivative, but it was basically just like a regular old L'Hopital multiplication problem. Only had to L'Hopital once. I guess the key there was noticing after you did the first derivative that there's good reducing to do to get rid of the denominator. If you missed that, you'd have been L'Hopitaling for a long time because you're not going to get rid of the denominator any other way. But that's that. Victoria, are you happy with what we did there? Yeah? Yeah, okay. That's okay. Mia. Same section, number 45? Okay. Sure. It's a little. Okay. So again, first want to check to make sure this is in the form for L'Hopital. If I do a direct substitution, x to the third, it becomes infinity. E to the negative x becomes 0. I have infinity times 0, so that's L'Hopital. Here, I don't have to do anything special to rearrange this to get into a division problem. I can just rewrite the negative exponent as a reciprocal, and I'm ready to L'Hopital this up. The catch is, looking at this, I think I'm going to have to do probably more than one L'Hopital, but that's okay. The reason I say that is that I have that x to the third up there, right? It's probably going to take more than one differentiation to get rid of all the x's in the top. So e to the x squared is a chain rule problem. So the derivative of the outside is just the derivative of e to the x. So I have e to the x, or e to the inside. And then the derivative of the inside is 2x. And I noticed that, all right, well, that speeds up the process a little bit to do some reducing there. But if I try to direct substitute again, I still end up with, like, in this case, it'd be like infinity over infinity. So I still got a L'Hopital one more time here. So the derivative of 3x is just 3. That's awesome. The derivative of 2e to the x squared is going to just be 2e to the x squared times 2x again. And at that point, I'm good to go. If I direct substitute, I end up with like 3 over 0, which is, or I'm sorry, 3 over infinity, which is 0. Yeah. Yeah, I mean, like, e to the positive whatever, if I'm going to infinity, is infinity. It doesn't matter what's going on in the exponent as long as it's a positive number, right? Or as long as it's like an increasing function, I guess I should say. Is that okay there? Sure. So it sounds like you were already you got to the point where you just weren't sure what to do with the e to the x squared. I mean, the way to think about it here, Mia, using our limit rules, so we have like 4x e to the x squared, right? So I can do like the limit as x goes to infinity of 4x times the limit as x goes to infinity of e to the x squared. And I can do like 4 limit infinity of x times e to the limit as x approaches infinity of x squared. So this is just like 4 times infinity e to the infinity, which is still just like infinity. Sure.
So you said that e to infinity would just be infinity. Isn't the indeterminate form is like infinity times infinity? So it's like
Right, but that's in the numerator. This is in the denominator. So it's okay. That's the catch. If that, I know that's not very satisfying, Victoria.
so if it's in the denominator, it doesn't matter.
Correct. It's still just like little over big goes to 0. Mackenzie. 4 point which one? 4.3. And then which number? 42. Thank goodness that thing took a little break. 42. Oops. Okay. I have a lot of directions here, so I'm going to take all the problems so that I can have the directions there. All right. 42 says find the intervals of increasing and decreasing. Then find the local max and min values, and then find the intervals of concavity and the inflection points, and then use all that to sketch your graph. All righty. So 42, first thing I should note is that the domain for my f of x is it's going to be all real numbers, right? Anything to the fourth is going to be a positive value. And then I can take the log of positives because I have just positive plus 27, so still positive, right? So anything I can plug into this, that's great. All right. So to find increasing, decreasing, I need to look at the first derivative. So that's a chain rule. The derivative of a log is 1 over the insides, and then times the derivative of the insides. I note here that the domain is also all real numbers because, again, the denominator can never equal 0. Since it's a rational function, that's the only place I have to worry about. So to find my perspective places where, or to find the rest of my critical values, to find my maxes and mins, and to find the boundaries for my increasing, decreasing, I'm just going to set the derivative equal to 0. Since this is a fraction whose denominator cannot equal 0, all I really need to do is figure out where the numerator is 0, which can only happen at 0. Everybody cool? All right. So I'll just do my increasing, decreasing test. So I'll take the first derivative at -1 and the first derivative at +1 and just see whether they're positive or negative. I can see right away that the top is going to be negative, the bottom will be positive, so that's negative. And for 1, the top would be positive, the bottom would be positive, so that's going to be positive. So for part A, we're going from -infinity to 0, and that's decreasing, and then 0 to +infinity, that's increasing. Part B, if we go from decreasing to increasing, that means that x equals 0 is a local minimum. And I don't know if they wanted it as a coordinate or what they wanted here, but the point would be 0, 1 over 27. I'm not sure with the way they asked for the values, so they want the 1 over 27. C is asking about concave up and concave down, as well as the inflection points. To do that, I need the second derivative.
How did you find the now?
I just plug 0 into f of x.
Okay.
Oh, sorry, that's not 1 over 27. I plugged into f prime, dum-dum. What do I got here? So I'm plugging 0 into that, so it's just going to be the natural log of 27, whatever that is, 3-ish. All right, second derivative, I'm going to have the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Oh, what do we got here? I have 12x to the 6th minus 16x to the 6th. So that's going to give me minus 4x to the 6th. And then plus 12 times 27 is 81 times 4. So that's 324 x squared over that stuff. I think I did that right in my head. 12 times 27. Someone got a calculator handy? Is that 324? I think so.
No, I think we wrote 4x cubed twice instead of 4x squared.
Oh. Oh, yeah, thank you. So that's not right. So I have the derivative of no, that is right. That's the derivative of the bottom times the top. So that's right. Yeah, okay. So negative 4x to the 6th. And then it was plus 324x squared, I think. All right. Again, the domain for this is all real numbers. I can tell because the denominator, again, cannot be 0. So all I need to worry about for changes in concavity, since the f was continuous and f double prime is continuous, all I need to worry about is where the second derivative is 0. And I know that's only going to be equal to 0 where the numerator is equal to 0. Oh, sure did. So we'll start by factoring out a 4x squared. So there's that. I notice x to the fourth minus 81 is a difference of 2 squares. And that's x squared minus 9 is also a difference of 2 squares. Yowzer, yowzer, yowzer. And when I set each of these equal to 0, I get 0, I get 3, I get negative 3, and I get no real solution there. So those 3 values are my potential inflection points. Now I'll do my concavity test here. I'm going to simplify the process of doing this, though. I'm going to observe that the denominator is going to be always positive regardless of what I'm plugging into it. So I'm just going to worry about whether the numerator is positive or negative. And probably when I look at the numerator, I'm going to look at it in this form. Or, yeah, that feels good. So if I plug in negative 4, I have negative up front, positive, positive, so that's negative. When I plug negative 1 in, I have negative up front, negative, positive, so that's positive. When I plug positive 1 in, I have negative, negative, positive, so that's positive. When I plug 4 in, I have negative, positive, positive, so that's negative. So that makes 3 or negative 3 and positive 3 inflection points. 0 is nothing because there's no change in concavity there. So it's not an inflection point because it's positive followed by positive. So it's probably like one of these things, right? Where there's no real change in concavity. It just like goes or whatever. All right. And then it expects us to sketch a graph after this now, right, Mackenzie? All right. So let's start by plotting some points. Before I get going, here I'm probably going to go ahead and find the coordinate for these. So if I go back to f of x, I'm going to do the natural log of 3 to the 4th. I'm going to not worry about the negative sign because it's going to get gobbled up by the 4th power anyways. Yeah. So like 4.7, so let's see. 1, 2, 3. 1, 2, 3, 4, 5. So I have like this and this. So there's my inflection points. And then natural log of 27 was 3.29. So there's my local minimum. Okay. So we're decreasing this whole section, and then we are increasing this whole section, and then we are concave down here and here. and then we are concave up here. So like this section of the graph, I can tell is going to look like that, right? That's decreasing from zero or from -3 to 0, and then increasing from 0 to 3, and it's concave up both of those places. And then this has to be then concave down and decreasing. So it's going to like look like that now. And like that now. So kind of like a shruggy face or something. Is that okay, Mackenzie? Okay. Sure. Again, lot to sort through on that problem, right? Asked us to do a bunch of stuff. The hardest part about it is keeping everything straight, right? What am I plugging into? What am I getting? What do I set equal to 0? What does that tell me? It's just a lot of stuff to keep track of because we are using f prime, and f double prime in the problem. We're solving f prime and f double prime equal to 0, but we're plugging those solutions sometimes back into the derivative or second derivative when we're doing our test, but we're plugging those answers back into f to get the coordinates for the points that we're plotting. So just kind of, just got to be careful about what you're doing and where you're plugging stuff into, right?
So you didn't do anything with the intercept.
It didn't ask us to, so I elected not to worry about it. In this case, there's no x-intercepts. That's nice. Probably could have determined that by looking at this thing. Since your x is always going to be bigger, or the argument inside your logarithm is always going to be greater than 1. So like I can kind of tell that it won't have any x-intercepts. And the y-intercept happened to be the same location as our minimum, so we graphed it anyways, just without even trying. All right, should we do 4/8 here? Get it done? Okay. You guys are super helpful. All right. So 4/8 is about Newton's method. What Newton's method is, it's a technique that we can use to approximate solutions of an equation. Okay, so this is a technique to solve an equation. Now, you're not going to get the exact solution. You're going to get an approximate solution. But the nice part about Newton's method and the approximate solution you're getting is you can do Newton's method as long as you want and continue to get a more and more accurate answer. So if you need 10 decimal points of accuracy, you can just do Newton's method a bunch of times, and eventually you'll get your 10 decimal points of accuracy. So it's actually a really excellent method. Most of us that have the standard non-CAS TI calculators, that's the algorithm built into, like, when you find the 0, that's really what the calculator is doing. Well, I shouldn't say, I don't know what the code is, but I surmise that that's what the code is when it's, or even like finding a maximum or minimum. I suspect the code is to solve, or what it's doing is it's doing a derivative, setting equal to 0, solving with Newton's method and then evaluating that in the endpoints of the interval that you chose to find your max or min, I suspect is something like that, is some version of Newton's method. So just a geometric explanation of kind of what's going on. So let's say you want to solve some equation f of x equals 0. So that's what we're looking for here. We're looking for this, which is our solution to f of x equals 0. Okay. So this is the same as, looking for the roots or x-intercepts for the function, right? So what we're going to do is we're going to start with a guess. Something that seems like it's reasonably close. So how could I tell that by a guess? I'm just evaluating like how far this is from 0, right? If it's pretty close to 0, it's probably a pretty good guess as a start. Everybody's cool with that? Okay. What we're going to do then is we're going to create a tangent line to f of x at that point of our guess. So that's drawn here in pink. And we're going to find where that tangent line crosses the x-axis. We're going to use that to generate a second guess, and we're just going to keep repeating that process over and over and over again. Mackenzie. So this is a guess at the solution. So we want, ideally, the closer this is to 0, the better our guess is. But like kind of almost anything will be fine. Paul.
Does it matter if it's in front of our result?
Nope. Well, if you were down here, it'll work the same. So it doesn't matter. Everybody okay with that? So let's do an example, right? That's the gist of what we're doing. This is the kicker here. This is the thing that we need. This is how we find that next guess. So the x to the n plus 1 is our next guess. That's equal to the previous guess minus f of the previous guess divided by f prime of the previous guess. Okay. And then what's going to happen is if we've chosen that initial guess appropriately, the limit as that n approaches infinity, the more guesses we get, or the more guesses we make, that potential or that approximate solution approaches the actual solution. All right. Let's start here with an example, and I'll circle back to another situation where I'm talking about like how having to be careful about our guess. All right. So x2, our second guess, is going to be the first guess minus f of the first guess divided by f prime of the first guess. Everybody agree with that? That's just me filling in the formula. So if f of x is the polynomial that's given, f prime would be 3x squared minus 2. So this should be 2 minus 2 cubed times 2 times 2 minus 5 divided by 3 times 2 squared minus 2. Everybody happy with what I did there? and now I could grind this out on my calculator. Or, here's what Mr. Kulik would suggest. Let me show you how to do this on your calculator so that you can just press enter a bunch of times and get all the guesses you would ever want. So if you have your calculator with you, I'd encourage you to take that out and follow along. And I'll show you kind of how to set this up so that you can just like bang out a bunch of guesses in Newton's method after one initial setup. Everybody's cool? So I'm going to start by typing in my guess and pressing enter. So just start with the guess and press enter. Now I'm going to set up this equation. So everywhere where there's before that, I need to type my function into y1. So let's do that also. So I'm typing my function into y1. In this case, that's x cubed minus 2x minus 5. I'm not going to bother with the derivative. I'm going to let the calculator handle all the calculus for me. I'm just going to type in the original function into y1. I'm going to type in the initial guess and press enter. Everybody's cool? So now I'm going to type this formula, but in place of x1, I'm going to use the ants command. So I'm going to press second and the negative sign, and I'll do subtract. I'll do alpha y equals, and pick the fraction command. And now I'm going to do y1. So I'm going to press vars over to y vars, pick function, pick y1, and I'm going to do y1 of ants. And now I'm going to type in the derivative evaluated at ants. So to do that, I'm going to press math. I'm going to scroll down to n derive. So I have to indicate the variable which I'm differentiating with respect to, which would be x. I'm going to be differentiating y1. That was the function. So I'll go and get that again. And I'm going to evaluate that derivative at ants. Y equals the function, x cubed minus 2x minus 5. Okay, so we have that set up. Is everybody cool with the setup? Did you find the commands? If you go back and rewatch the video at this place, you can see like the mouse going to the buttons and stuff. It makes that nice. Okay, I'm going to go ahead and press enter. There's my first guess. I press enter again. There's my second guess. Because I've recorded as ants, take good advantage of that ants. I can just keep pressing enter, and it'll keep giving me the next one in that sequence, which is like really unbelievable if the textbook asks you to find like x5 or something, where all you need to do is set it up and then just press enter a bunch of times. How nice is that, Mr. Kulik? Like, talk about a time saver. Imagine what Mr. Kulik had to do as a student before these nice calculators that could do this all in. This was a nightmare, having to keep track of all the decimals and keep plugging them all in, right? Because setting up this way, did I do any rounding? No, I'm using the entire calculator's float memory of whatever that decimal is, right? I'm not just using the decimals you can see on the screen. I'm using all the decimals that are stored in the calculator's memory, all 255 digits of them or whatever, which is pretty rad. Does everybody feel cool about what we did there? So if I go back and I answer this question, right, this first answer is 2.09 repeating. That's my x2. And then x3 is going to be, what was that? 2.094 yada, yada, yada. I'll type in all the decimals. What do you think? That's kind of the gist of it.
Is that important to not round? Like, if I said 2.09, that'd be wrong.
If you did like squiggles, you'd probably be okay. If you write a straight equal sign, probably not. I think the directions would probably tell you like round to what X decimal place. I would say if it doesn't, though, I would just write out my entire calculator display, just to be safe. All right. Another application, we can use Newton's method to approximate the answers to radicals. So for example, if I want the 6th root of 2 correct to 8 decimal places, yowzer. Okay, so first thing I want to do is translate this into a function. X to the 6 needs to equal 2, right? That's the same thing as the 6th root of 2. Everybody agree with that? And I'm going to really turn it into the equation then, x to the 6th minus 2. So this is my f of x. Now I'm just going to go to my calculator. So y1 is x to the 6th minus 2. And now I need to type in a guess. Well, what do I know here is that somewhere between, the answer for this is going to be between what two numbers?
0.
What's the 6th root of 1? 1. Okay. And the 6th root of 2 to the 6th? It's 2. So 2 falls between 1 to the 6th and 2 to the 6th, correct? Which one is it closer to? 1 to the 6th, right? So my initial guess would be 1. Seems like a good one. Everybody agree with that? Doesn't have to be, you don't have to get too fancy about it. 1 should be good enough. And then guess what? I'm not even going to retype all that stuff. Since I already did it once in my calculator, I'm just going to scroll up, press enter, because everything else doesn't matter. So there's my first approximation. My second approximation, so 1.1, I have 1 decimal point correct there. Press it again. So I have 1.22, I have 2 decimal points correct. Everybody see how I'm figuring out how many correct I have? If the decimal points are identical from the previous one. So I have like 1.12 is the same for both of them. So that much is correct. Do it again. So 1.22 is correct. And actually I think 1.224 I'm up to 4 decimal places. Press enter again. And then 6, 2, so it looks like I'm up to 6 decimal places, or 7. Probably one more ought to do it. That looks like that'll do her. Is everybody cool with what we did there? How much of a time saver is it, this calculator setup I've shown you? Imagine doing that annoying thing by hand where you cycled through 6 iterations of that. Yes.
So how do you know when you got into like the correct 8 decimal?
So all I'm doing is comparing my answer to the previous one, and everything that's identical. So like the ones are identical, that's correct. The first decimal place is identical, that's correct. The second decimal place is identical, that's correct. And I just count down. If I'm comparing it to the previous answer and the decimal places are identical, those decimal places are correct then. Or the first set of identical decimals. Does that make sense?
Right. So that.
So if I scrolled back to the very beginning,
You could really just set your calculator a bunch of times and then click it again and compare the top and bottom.
yeah, so this was x1, I'm sorry, this is x2 and x3, right? If I compare these, well, 1 is correct, 0.1 is correct, but the next decimal point is not because it's different.
And then when I put, like when I did the, like copied the equation and then with the answer, that gave me those, but it's like 1.122.
Yes, so the next one, if I compare them, the 1.12 is correct because up to there is the same, but the next decimal point is different. So we have 2 decimal points that are correct there, and we can just kind of keep going comparing our new answer to the previous one. Taylor.
How did you decide what number to use first?
The starting value?
Yeah.
Okay, so I know that like 1 to the 6th is 1, and I know 2 to the 6th is like, what is that? Is that 1? No, that's 64, right? Something, anyways. And 2 is somewhere between, right? It's somewhere between 1 and 64. Everybody agree? Which one is it closer to? 1. So that would be the guess I'd start with.
Okay.
So I'm just looking at the 6th powers.
Okay, yes.
My number 2 is between the perfect 6th, 1, and the perfect 6th, 64. Closer to 1, so I'll just start my guess with 1.
Okay.
Could have you started your guess with like some other number and been fine? Yeah. It would have just taken longer, right? The closer you are, the better, less time it takes. But like you could have started with 7. It just might have taken a little while. Is that okay with you guys? All right. So the one place we have to be a little bit careful about when we're not given a guess is our choice of guess. So look at this graph here. We started with our x1 as this point. I drew my tangent line, I get this point. I make my new tangent line, I get this point. What's going on here? We're getting further away from our answer. You guys see that? So sometimes, if your guess isn't close enough, bad things can happen, right? So if you start seeing no convergence in your Newton's method, what should you do? Start over with a new guess, right? Start over with a new guess. That's all we're saying. So if you've, like, this is an example where you do this and it's just going to spin out of control, going all over the place, especially a function that's like got a lot of action going on, like there's a lot of maxes and mins going on right near that solution that we're looking for. You're going to have to get pretty close to that. You're going to have a pretty good guess initially to catch something like that. Okay, let's look at one more, and then we'll be done with this section. Sound good to you guys? All right, so here we're looking for the solutions to the equation cosine x equals x. So I start by turning it into the equation equal to 0. My y1 will then be cosine x minus x. Now I have to think a little bit about a guess here. What do you think would be a decent first guess? Well, without assuming this is a non-calculator question where I can't just like look at the picture of cosine x minus x, this is what I would use as my to indicate what to do or to come up with a guess. I would sketch in a graph of so this is a graph of cosine, right? This is like pi over 2. Everybody's cool? And then I'd sketch in a graph of y equals x. So the point we're looking for is this one, correct? So pi over 2 is 157. It's going to happen before that. I would just use 1 for my initial guess. Is everybody okay with how I came up with that? Without a calculator? Just kind of knew what cosine looked like, knew what y equals x looks like. Just trying to find that intersection. It's going to happen somewhere in between 0 and pi over 2. What's the decent number in there? I would pick 1 because, well, I don't want it to be a complete pain in the butt. All right, so I put that in there already, cosine x minus x. 1 is my first guess. And then I'll grab this guy. Oops, what happened here? Got to make sure I'm in radian mode. Oops. Now I'm in some trouble. So I got to redo my first guess and then go back. There we go. So I do this. It says correct to 6 decimal places. Sorry. So I first guess, or first answer, I go to the second answer, I have 1 decimal point correct, right? The 0.7 is correct, but not after that. So I go to guess 3, and I have 3 decimal points that appear to be correct. I'll go to guess 4, and I have now 8 decimal points that are correct, so I'm good. Everybody cool? So what do I have? That's good enough. And which one was that? That was our 4th one, I think. No, that's our 5th one, I think. Yeah, because the first one was our first one. It's pressed enter 4 times, but 1 was our first one. What do you guys think? Is this a good one? We can do this, right? As far as an exam question goes, the directions would be such where it's like, show the initial setup, like we did here, to find the first point, and then you just use your calculator after, right? If I wanted x6, that would be enough. The directions would be, like show your work to find x2 and use your calculator thereafter. That seem fair? Okay. What do you guys, this was pretty easy, right? So like, remember on the previous test where I had said like write this equation in terms of k? And you had like some cubic equation that you couldn't have been able to solve algebraically. Newton's method, right? That's how you would actually do that by hand. That's how the calculator is doing it when you're using the 0 command or the intersect command or whatever you use there. Or some version of this is likely what it's doing. I haven't looked at the code to know what it's doing, but that's my suspicion. That feels good for today, guys.